All right, so moving on now to conservation of energy with rotation. If we look at this, it's going to be the same as conservation of energy without rotation, but we're going to have an additional term now for the fact that we can have energy, kinetic energy associated with our rotational motion. So what we want to show here, or what we want to talk about, is how we're going to change our kinetic energy when we do conservation of energy. So our total kinetic energy is not going to just be our translational kinetic energy anymore, KT. It'll also have a KR. So KR is our rotational kinetic energy, and KT is our translational kinetic energy. And so KT is the one that we've dealt with all semester, where we have it's equal to 1/2 m times the velocity of the center of mass squared, where V sub cm is the speed of the center of mass. So that's the speed of the center of mass of the object. And now we have K rotational. And in rotational world, remember our equations are the same, but we use the analogous term in rotational world. So instead of the linear inertia, the measure of the linear inertia mass, we want to use the measure of the rotational inertia, which is I, our moment of inertia. And instead of our rotational speed, our linear speed, we want to use our rotational speed, omega. So 1/2 I omega squared. And we want to recall from what we just did with rolling motion that we can write V sub cm is equal to omega times r. So we can actually write omega as the velocity of the center of mass over r. And this is an important problem solving thing to remember because it allows you to relate your omega here to your velocity of your center of mass, or your speed of the center of mass here. And so your KT is related to your KR. And so that becomes an important result. All right, the other thing that changes when we do conservation of energy is when we talk about gravitational potential energy being mgh, this becomes mg times the height of the center of mass. So that's a commonly missed step, where it's the height of the center of mass is what matters. So those are our main changes to conservation of energy with rotation. So in order to now look at how our steps will work, basically again, you're going to visualize the problem, as we always do, and you're going to decide on your initial. So you're going to visualize the problem, and then we're going to decide on our initial and our final for this idea that our total initial energy would equal our total final energy. Recalling that energy is a scalar. So there's just a single equation of total initial energies equals your total final energies when you include everything in your system. So step 2 then, right, we write out our initial and final energies. And this is going to be where there's one thing to remember when we do problems with conservation of energy with rotation. So we're going to write out our initial and final energies. And I'll write this as a key note here. That's very different than something we've encountered before in terms of conservation of energy, because we didn't have to worry about rotational motion. So we have 2 types of rotational motion. One, something might be free to rotate, meaning a ball rolling down a ramp, or it might be something that's pivoted. Say I pivot this pen and it's able to rotate this way, in which case I'm constraining its motion by pivoting it. So if we look at the first case, say something that's free to rotate. So it's free to roll or move, meaning that it's not in some way constrained. So I'll just say here, not pivoted for problem recognition purposes. Then you're going to use K total is going to be equal to both your translational kinetic energy of the center of mass and your rotational kinetic energy. On the other hand, if it is pivoted, you've actually now constrained the motion of the center of mass. And so it can be shown that in this case, you only want to say K total is equal to K rotational only. So in this case, you don't use the translational motion of the center of mass if it's pivoted. So that's going to be a very important application. When you look at a problem, you have to decide when you're writing out your initial final energies, is it something that's constraining the motion of the center of mass? Is it pivoted? And if so, you only use the rotational kinetic energy. It's all in that rotational term. And then, or is it something that's free to rotate? Say a ball rolling down, the hill, a block flying through the air, anything like that. The other note here that I will put to remember is to use the height of the center of mass for the UG. And then, as we usually do, you're going to set your sum of all your initial energies equal to the sum of all final energies. You're going to solve and check your answer.